Questions about anything from last time? So I finished last lecture mentioning that if you Google the Wikipedia page about Fourier transform, they list the sort of three most common versions in books. And my favorite version for using it in a day-to-day manner is number 2. I think number 2 is the easiest for solving PDEs or any kind, or if it's get used to solve differential equations. Because when you take the formulas for the Fourier transform of a derivative, all that comes out is, let's see, what it integrate by parts, and you would get an ISX comes out, an IS. So when you take the Fourier transform number 2 of f prime, it's I times S times the Fourier transform for f. And that's particularly easy to remember for solving differential equations. If you use number 1 for that, well, there'd be 2 pi's coming in, and they'd be kind of annoying. But there's other reasons why number 1 is useful for today's business in the theory. And so number 2 here is good for theory, especially the theory of the inverse Fourier transform. And I'll explain why that's the case. And so when I do theory in the next couple days, I'm going to use number 1 version. When I go back to solving PDEs and using the transform, I'll use number 2. And number 3, I would say it happens. It happens in some books. And I can see why, because when you're talking about the Fourier transform, you don't even want to think about where the 2 pi should go. And so when you're looking at the Fourier transform, you write it like that. The derivative formulas are easy, etc. But then when you have to talk about the inverse, the 2 pi has to come back in and go somewhere. And so then that's why it's in the inverse, but not the original transform. So this happens in books, and I can see why. It's because they keep forgetting to put down the 2 pi. Okay, so for the next couple lectures, I'm going to use version number 1. And so here's the reason version number 1. It's basically 3 things. It's good for theory because, conveniently, the Fourier transform of this famous bump function, e to the minus pi x squared, is basically itself. So it would be the function of s, e to the minus pi x s squared. So that maps that thing to itself, and that's a very important feature, as we'll see in a minute. So that's one good reason for the theory version. Another important thing is something called the Plancherel identity. The Plancherel identity doesn't have any constants in it. The Plancherel identity is kind of like the Parseval's identity for Fourier series, but it's the L2 norm of f squared is the same as the L2 norm of f hat squared. And that's a very critical thing. So there's no constant in here, no constants involving pi's. If you use the other 2 versions, you'd have constants. It's just a 1. Okay, so that's nice. That means that the Fourier transform is an isometry on L2. So in this Plancherel identity, F is the L2 norm. And that would be equal to the integral from minus infinity to infinity of absolute F squared dx, and then you take the square root of that. Sorry, Mark, on the final exam, you'll be using Fourier transform number 2. So on the final exam, and I'll give you a formula sheet. Okay, so the name Schwartz was in the title of the lecture today, and I should mention that there's two Schwartzes in the subject. Schwartz with a Z, pronounced the same way, or maybe that's Schwartz, is the German guy. And in complex analysis, there's the famous Schwartz lemma. And a couple other famous things he did. He's in my family tree. If you go back to my advisor's advisor, etc., you run into Schwartz. His name was Augustus Schwartz. But then the Schwartz I'm talking about here today is with the TZ. He's a French person. And he had a breakthrough in discovering the theory of tempered distributions, which became very important in analysis and study of partial differential equations. So his name was Laurent Schwartz. And he discovered and studied tempered distributions, and especially showed how useful they were in extending ideas about the Fourier transform. Okay, so I'll tell you what the Schwartz functions are. They're very simple to define. Script S is going to be the space of Schwartz functions. It's a linear space. On R. And it's the space of rapidly decreasing functions at infinity. Sometimes it's called that. It's the space of, and you'll see how rapidly decreasing functions. They decrease so rapidly at infinity that you can basically do anything you want with them when you're integrating. You can differentiate under the integral sign, you can multiply them by things like polynomials, and still integrate them. So they're the rapidly decreasing functions at infinity. And here's what they are. They're C infinity smooth functions F, so infinitely continuously differentiable. Such that you differentiate F any number of times you want, and then you multiply by a power of X, and that would go to, let's see, the limit as X goes to infinity or minus infinity. either end. You take a derivative as big as you want, and then you multiply by a power as big as you want. And those go to 0 for all n and m. Let's see, positive integers, well, even 0 for all n, m equals 0, 1, 2, etc. Okay, so they really shoot into 0 as x gets big. And so we've seen one example so far, namely e to the minus x squared. That's a Schwartz function. If I differentiate that, it would just bring out powers of x. And if I multiply it by powers of x, it would make the powers of x even higher. But it dies away so fast that it kills powers. And it's integrable, even if I differentiate it and multiply by polynomials. It's a pretty simple exercise. I won't do it. In fact, you'll notice I'm not going to do all the details in some of the things I say today, because I just want you to understand the main points about Fourier inversion. So it's a simple exercise just using the definition to see that a function is in the Schwartz space if and only if it's C infinity smooth and these things are bounded. So the soup on the real line of take an nth derivative and multiply by a power, that soup is finite for all n, for each n comma m, as the n and comma n's go from 0 to infinity. Okay, because if you had that soup finite, let's see if you want, yeah, I'm not going to do that. It's a pretty straightforward thing. One direction is obvious from the definition. The other direction, you got to think about a little bit. All right, so there's a bunch of easy facts that I'll just tell you without boring you with the demonstrations. They basically follow from the definition. Let's see. One is that if f is in the Schwartz space, then f prime is in the Schwartz space. That's kind of a no-brainer. And if f is in the Schwartz space, then x times f is in the Schwartz space. Also a no-brainer from the definition. But a bigger fact and the reason Schwartz invented this thing is if f is in the Schwartz space, then the Fourier transform is in the Schwartz space. And that takes a little bit of work. Okay, so I should have mentioned that for theory days like today, the Fourier transform of S is going to be integral from minus infinity to infinity of f of x e to the minus I 2 pi sx dx. So that's number one Fourier transform. Okay, so if you want to demonstrate that bigger fact, well, there's a bunch of properties that are relevant. So I'll call these important properties. Of the Fourier transform on S. Let's see, one. We're going to write f hat of S is the Fourier transform of F. If I take F and translate it, x plus h, then the Fourier transform would take that. Let's see, it takes it to e to the 2 pi I s h f hat of S, 2 pi-ish. So if I shift a function by translating it, then it's going to do something weird to the Fourier transform. It doesn't shift the Fourier transform, it multiplies it by something. It has a unit modulus, so it doesn't change the norm or anything when you calculate that kind of thing. Okay, that's one simple thing. And to prove it, you would just write out the formula and then do either a change of variables or an integration. In this case, it's a simple change of variables, a shift, and it just pops right out. So I won't bore you with the details there. Let's see, and the funny thing, there's always a dual formula. If I multiply a function by e to the 2 pi x h and hit it with the Fourier transform, then that shifts the Fourier transform. So there's sort of a mirror duality going on here in all these formulas. 3, if I dilate a function, so say f of delta x, then that would be, this should kind of feel like when I was messing around making good kernels, and it very much is related to that. It will be. So think good kernels right there. That's a very simple thing to show. You write out the formula, and then you do a change of variables and call u the delta times x, do the change of variables, and that just pops right out. So that's a very simple thing to check. With this version of the Fourier transform, when you do the integration by parts argument that I've done before, instead of an is coming out, a 2 pi is comes out. That would be annoying if I was doing differential equations. For theory, it's not so bad. Okay, you've seen me do that before using integration by parts, and for Schwartz functions, the tail end of the integrals go to 0 really fast, so they don't contribute anything to that calculation, really. And let's see, one more. The mirror one for this, I'm going to have on this side the derivative of the Fourier transform. And then on this side, it turns out you get the sort of the mirror dual formula, minus 2 pi I x times f of x. Okay, so basically if you use those facts, these imply that bigger fact. So these can be used to see that the Fourier transform takes the Schwartz space into itself. And the proofs just involve changes of variables and integration by parts. You write the formula. Change variables or use integration by parts. It's kind of an obvious change of variables. Use integration by parts when there's derivatives. And the rapid decreasing at infinity means the tail ends of the integrals don't have much of an effect. Okay. So the one thing I do wanted to be careful about doing today is here's a important, the key property. Is that Fourier transform of e to the minus pi x squared is itself. This is going to be an easy thing to show, amazingly. And let's see, step one in showing it. First I want to show you it's a real valued function. I claim Fourier transform of e to the minus pi x squared is real valued. Let's see, why is that? Because, let's see, integral from minus pi, infinity to infinity of e to the minus pi x squared. And then here I would have e to the I to, minus 2 pi sx dx. Okay, this is, by the way, this is even. And this is cosine 2 pi sx plus I sine 2 pi sx. And the cosine one is even, and the sine one is odd. Okay, so when I integrate the even first function times the odd sine function, of course, and it's a symmetric interval, that's going to be 0. So this is actually going to be equal to 2 times the integral from 0 to infinity of e to the minus pi x squared cosine 2 pi sx. Kind of like a Fourier, kind of like a Fourier cosine integral. So sure enough, that's a real valued thing. Step 2, I want to show you it satisfies a differential equation. Kind of an easy one. Let's see, what is it? Step 2. Let's write f of s equals this Fourier transform. That's going to be equal to e to the minus pi x squared hat. I claim that f prime satisfies a simple ODE, namely f prime of s is equal to minus 2 pi s times f of s. that won't be hard to see. So this is going to be step 2. Oh, let's see why this is the case. Okay, so I'm going to have f of s is equal to, let's calculate. It's going to be d by ds of that thing I just wrote. It's going to be a regular derivative, ordinary. Integral from minus infinity to infinity of e to the minus pi x squared e to the minus I x e to the minus I 2 pi sx dx. And I can put that derivative inside there. And especially since it's rapidly decreasing at infinity, you can differentiate under the integral sign. And let's see, when I do that, so if I wanted to prove that I could do this, I'd write out the difference quotient, and I realized that I would get uniform convergence on a big finite interval, and I could bound the tail ends very easily and show that the thing converges nicely. So I'm going to avoid doing that kind of argument over and over again here today. But when I differentiate, I'm going to get, let's see, the derivative of that thing, when I use the chain rule, is minus I 2 pi x. I'm differentiating with respect to s, e to the minus I 2 pi sx. So that thing right there is d by ds of e to the minus I 2 pi sx. If you don't like doing that with the complex exponential, you could write it in terms of sines and cosines and see that sure enough that's a true formula. But I guess we've done it enough that we're comfortable doing it with complex functions now, especially the complex exponential. Okay, so look what I get when I do this. I can pull the I out in front. And then I want to do integration by parts. So this would be integral from minus infinity, and I'm going to have here minus 2 pi x e to the minus pi x squared. And here I have e to the minus I 2 pi x dx. This thing right here is the derivative of something. This is going to be, look at it, yeah, it's the derivative of, this is phi prime of x, where the phi is e to the minus pi x squared. So what I have here is I times the Fourier transform of a derivative. And from the formulas above, I forget what number it was, but that would the Fourier transform of a derivative is I 2 pi s times the Fourier transform of the function. So, what do I get? I get minus 2 pi s. And that phi hat of s is my Fourier transform, f of s. So that's all there is to getting the ODE. And now I'll solve the ODE using Math 262. And that'll determine what f is. So the next step is to solve the ODE. And it's a simple linear ODE. Let's see, so we got f prime of s. When I put it on the other side, I would get plus 2 pi s 2 pi s times f of s equals 0. That's a first order linear ODE. So in Math 262, even 366, wherever you took it, the integrating factor, it's already in standard form, so it's a first order linear ODE in standard form because there's a 1 in front. So if there was a function in front of that derivative, I'd divide by it to put a 1 there. That puts it in standard form. And so we know there's an integrating factor. And let's see, it would be u of s is e to the integral of the function right here. Call that p of s. E to the integral of p of s ds. Well, that's would be e to the 1, let's see, integral of 2 pi s would be 1/2 2 pi s squared. So plus pi s squared. Interesting. And what you do with the integrating factor is you multiply the ODE, that standard form, multiply standard form ODE by the u, the integrating factor. And the reason you do that, then you get u, which is u times f prime plus 2 pi s f equals, fortunately the right hand side is 0 here, that's going to be nice. And the reason we chose this integrating factor was to make this the derivative of a product. That formula for the integrating factor was devised so that this would be, when you do the product rule, the derivative of the product. Okay, that's why we cooked it up. And that means u times f is a constant. So we conclude, since the derivative of that is 0, u times f is identically equal to c, a constant. And since we're dealing with a real function, it's a real constant. Okay, so we have what my u was e to the pi s squared times my f of s is a constant. And so the f of s is a constant times e to the minus pi s squared. And the last thing I have to do, I have to figure out the constant is, I can figure out the constant by plugging in s equals 0. So we'll determine constant, determine c by plugging in s equals 0. Let's see, f of 0, remember, that's the Fourier transform. So that would be equal to the integral from minus infinity to infinity of e to the minus pi x squared times 1, right? dx. Because this 1 would be e to the minus I 2 pi 0 times x. And guess what? That is a famous integral. You can calculate it. Remember, I calculated the integral of just e to the minus x squared using polar coordinates and was able to show that that was, I forget what it was. Was it the square root of pi or something? Anyway, with the pi right there, this turns out to be 1. You could demonstrate that using the polar coordinate trick I did back when I did this. So the area under that graph is famously equal to 1. Well, let's see. Here's the feeling. If you know the Fourier inversion formula is true on Gaussian bump functions, then it's actually true more generally, because you can always write a function as a linear combination of bump functions. So if Fourier inversion is true on these famous Gaussian bump functions, then it's true much more generally. Because you can approximate functions, especially Schwartz functions, by sums of bump functions. Lots of types of functions, especially Schwartz functions. And especially functions in S. By linear combinations of bump functions. Okay, that's not a proof, but that's the feeling. So let's see. This is a feeling. And the feeling is that we know Fourier inversion on a bump function now. And so the feeling is it's going to be much more generally true. And so the reason is, we've done this before, if I make a good kernel out of a bump function, which I've done in the past, let's see, phi of x equals e to the minus pi x squared. Then I would have phi sub epsilon. Remember how I did it. Phi sub epsilon is 1 over epsilon phi of x over epsilon. I've done this before. And recall, we did the good kernel business to show that when you convolve phi epsilon with a function, remember that stood for the integral from minus infinity. The bump shifted a little bit, f of t dt. Didn't matter what order you did it in. And then you approximate this by a Riemann sum. Which, if the thing is a Schwartz function, the stuff far out becomes negligible, and so you can turn it into a finite sum. And it's going to look like, let's see, when I do a finite sum, that's going to be an approximately a sum. I'll have phi sub epsilon of x minus a point. So t sub I, f of t sub I, that's a number, delta t. And because the thing is a Schwartz function, the tail end is negligible, and I'll make a finite sum. And those are bump functions centered at x's. So I have finitely many bump functions centered at x. And remember that this, we saw that this thing converges to f. So what I have here is that f of x can be approximated by this. And so f can be approximated by a sum of bump functions. And if we know the bump functions satisfy Fourier inversion, it means we know that f will. That's why we feel like this has got to be a true thing. And the key was understanding it on bump functions. Okay. And I emphasize that's a feeling, not a proof. Well, let's see. I don't want to get carried away today. Let's see. So an important lemma that I've already demonstrated is that if a f is in the Schwartz class, then phi sub epsilon, which is that bump function, convolved with f, tends to f uniformly on the whole real line. Okay, and I've done this in the past. When I made that bump into a good kernel, we did this. I showed it converged pointwise, but when the thing is a Schwartz function, it's easy to see that the pointwise convergence is uniform on the whole real line. So we did this earlier in the semester. Using the good kernel argument. Okay, so remember, an important point in this business now is that that function with the pi in it is convenient in that its integral underneath is 1. So that thing is the Gaussian function. Looks like that. E to the minus pi x squared. The area under that thing is 1. And if I take a bump, then I would get a thing, the area is still 1, but it would be concentrate the area underneath. It would concentrate the area around 0. So this would be the phi sub epsilon of x. The area under that one is also 1, but it's more concentrated at 0. So the area under the phi sub epsilon is also 1. And the homework problems you did were to show that this thing has the properties of a good kernel. So the things I did back earlier in the semester to demonstrate this thing are all ready to go with the last homework, homework 7. So let's see, if I wanted to show this, I would have phi sub epsilon convolved with f at x minus f of x. This one I'd write as the integral from minus infinity to infinity of let's see, where do I want the x? It doesn't matter what order I do this in. I think I prefer this one. Definitely. And then I have minus the f of x. And because the integral under that thing is 1, I can write it as an f of x here. So that f of x is a constant. And then you can play around and split that integral into pieces. One piece where the f's are small and the other piece where the phis are small. And I've done it enough times that I'm not going to do it again. So for a Schwartz function, it can be made incredibly small as in the tail end.